So in this video of Chapter 20, we're going to look at some practical applications of electrochemistry. We're going to look at batteries, corrosion, and recharging batteries. The first battery we're going to look at is one called a lead-acid battery. Lead-acid battery is the kind of battery that's in your car. They're the heavy batteries that are used in many automotive or like moving vehicle applications. The equations for how these work are actually listed on page 888 if you have this particular textbook, and you can see it involves lead oxide. I'm going to move this just a tiny bit closer here so you can see it a little bit better. And that is the cathode producing lead sulfate. And then you can see the anode actually uses solid lead, and then that makes lead go to lead +2 and loses 2 electrons. And if you look up the standard reduction potentials for these, and then you do the anode minus the cathode, then you end up with a voltage of 2.041 volts. And as you know, car batteries aren't 2-volt batteries, they're 12-volt batteries. And so to make this work just a little bit better than 2.041 volts, we take 6 of these and we stack them all together. And here's a really nice image of a 6 stacked together anode cathodes. These two colors represent 1 battery, 2 battery, 3 cells, 4 cells, 5 cells, 6 cells. And then we hook them together in what's called series, and then you can add the voltages together. And you have a positive and a negative terminal there. And this makes our 12-volt automotive battery. What makes a lead-acid battery like this really good is that it can be recharged, and you can put electrons back in. And so then when you do that, these reactions right here that take place in H2SO4 or sulfuric acid can actually run in reverse. And so you could drive electrons back in there, and then you could break up this lead sulfate and make lead, and then here you could make the lead oxide be the cathode once again. And so recharging that type of battery makes it super valuable, or a really practical piece. You can see a really nice grid view of how the lead anode, and then it's submerged in this H2SO4 electrolyte, and then here's the PbO2 cathode right here, and you can see the positive and negative electrodes. And the practical, like how you put this together and then shape that, is a huge area in chemical engineering right now, and just a way of making practical batteries that are the particular size that work in, whether it be a vehicle or whether it be in a phone. One of the places where there's just going to be astronomical growth over the next number of years. The next type of battery we're going to look at is a lithium ion battery. The lithium ion battery is the one, of course, that's inside of many electronic devices. And the anode for a lithium ion battery is actually carbon, and it's carbon in a particular shape. And if you remember our carbon chemistry, there would be a carbon at each one of these corners, and it would actually make a large structure like this that would just be sp2 hybridized carbons. So it would just be single bonded carbons all in a ring shape like this, with lots of unshared electrons then hanging around. The cathode would be a heavy metal oxide, usually cobalt oxide, that makes a polyatomic ion like this that lithium ions could grab onto, or lithium +1 ions would be attracted to. So the cathode would be this lithium cobalt oxide right here. Now the lithium ions are actually the electrolyte that flows between the anode and the cathode, and the lithium ions are sandwiched in between these carbon structures. And then they're also sandwiched between these lithium cobalt oxide structures. And if I zoom in on this picture just a little bit, you can see that the anode exists in layers, and then the lithium ions stick in between there, and then they would move from the anode to the cathode as electrons are lost from the anode and then gained by the cathode. What makes lithium-ion batteries so good is that, first of all, lithium is super light. If you look at it on the periodic table, it's one of the lightest elements on there. Atomic mass of 3. The lightest metal for sure. And then the other thing that makes it really good is that it has a really low standard reduction potential. 3.05. It's one really here at the bottom. And so then when you pair it with something like cobalt, for example, which is a little ways up here, you can get a really high voltage just for one cell. High voltage meaning like 3.7 volts. Just for one cell. And then of course you can stack those together in series just like you do with a lead acid battery, and then it produces lots and lots of voltage, or lots of potential difference. So the electrons flow from one place to the other, and then you put a load in between. And of course these are one of the most valuable batteries in the world, and making these a little bit safer for the environment, because cobalt's maybe not the best stuff to be throwing away. And also a little less expensive, because cobalt's fairly expensive to get compared to other types of things like manganese, for example, which is now being used. But manganese isn't quite as good at giving you the voltage as the lithium cobalt oxide version does. All right, that's a couple of batteries examples. We're now going to look at a couple of undesirable redox reactions. And one of the undesirable redox reactions in the world is called corrosion. And one of the things that you'd probably notice right away is that lots of metals down here usually have fairly negative half reaction standard reduction potentials, which means they're pretty easily oxidized. And then when they're pretty easily oxidized, they would become ions like this. And so all the aluminum cans in the world, or everything made out of aluminum in the world, really should oxidize just because it's in the presence of air. Because air contains oxygen, and oxygen has a much higher standard reduction potential than does something like aluminum. And therefore it should form Al+3, and it should be aqueous, and so it's like all aluminum should just simply dissolve because it's in the air. And technically it does. But aluminum then combines with oxygen to form aluminum oxide, and this provides a protective coating around all aluminum structures so it doesn't dissolve. It actually has like a special coating called aluminum oxide around it that just naturally forms. There are other types of metals that do this as well, like zinc, for example, and magnesium, for example, but iron has the same kind of issue, and it does not have a protective coating. Iron is fairly easily oxidized, you can see right down here, and then when it does, it forms iron+2 and loses 2 electrons, and this would be iron aqueous, and then that would go together with oxygen, and its protective coating is called rust. And this is what we think of as a traditional type of corrosion in the world. And as a matter of fact, you can see right here in this diagram that iron right here, when it's in the presence of a water droplet, may be enhanced by some chlorine ions from like salt in the road that would give it a better salt bridge, is really good at forming Fe+2, then joining with this oxygen and forming this brown colored rust. And you can see that iron then is the anode and the cathode is the oxygen in the air. So what do we do to prevent this? Well, many, many things. First of all, we paint our iron lots of times, and when we paint it, we don't allow the oxygen to get at it. Another thing we do is we galvanize the iron. And galvanizing simply means that we take zinc and we plate or coat zinc on top of the iron. And since zinc has a standard reduction potential that's just a little bit lower than iron, then zinc would be the thing to first oxidize, and it could do the same thing like aluminum does. And this zinc, since it would oxidize first, actually forms like a protective coating over the iron. And then the zinc and the iron become a battery in sense, where zinc is the thing that loses electrons and iron is not. And so you get like a zinc oxide coating on top of the iron, and then that's your thing that protects your iron. So galvanizing of iron is one way we've come to try to protect that. Another thing that we do in industry that you've probably never heard of is we offer cathodic protection of iron with something called a sacrificial anode. And so this happens lots of times underground or with species that are in water a lot. If you have an outboard motor, for example, you could probably find a sacrificial anode connected to it. And here's an example of a sacrificial anode in just a diagram form, where we'd have a pipe, iron pipe, and then connected to it we'd put a wire to a chunk of magnesium. Magnesium's standard reduction potential is way lower or way below iron, and so therefore magnesium at negative 2.37 volts would very easily be oxidized. And so in effect what we're making is we're making like a little electrochemical connection. Iron's standard reduction potential is negative 0.44. With magnesium being way below it, that would be the one that would be oxidized first, and so then the magnesium would just simply be eaten away, and it would become Mg+2 aqueous, and then the iron pipe would remain just Fe and would not be undergoing any oxidation at all. And so that you'll find like a chunk of magnesium lots of times wired or soldered or connected to your outboard motor, or if you ever dig up a pipe and see like a little extra chunk of metal next to it, it's probably the sacrificial anode that is just connected to protect the pipe from it being destroyed, or I should say oxidized as well. So the last part in this video we're going to look at is doing the opposite, recharging batteries, driving electricity into a reaction to make the reaction happen. And this has a fancy name. It's called electrolysis, or an electrolytic cell, and it takes non-spontaneous redox reactions and making them happen by driving electrons into them. We see this when we recharge batteries. So when we push electrons back into a battery to restore it to its original state, we're producing electrolysis to make that happen. We also use electrolysis to separate different salts or metallic ores. We usually do this in a molten or melted salt, and we usually drive electricity into it, so then things gain electrons and then become their actual metals or nonmetals. And then the third thing we use it for is to plate or put a protective coating around something. One example of this is what we call silverware, and silverware usually doesn't actually have silver on it unless it's really expensive. It's usually got nickel on it, and so here's an example where we have a nickel anode right here, and then we have an object made out of steel right here, which could be a fork or a spoon or a knife, and then we run electricity into here, which causes some nickel ions right here to be plated onto the steel object. That's what we mean by electrolysis when we're doing plating something onto an active electrode. So we'll look at separating these salts and metallic ores just a little bit more in our next video, and we'll look at some quantitative aspects of this and ask how much electricity will it take, or how many electrons will it take to make something actually separate. Hopefully in this video, though, you've learned a little bit about batteries and how there's an anode and a cathode to each one of them in the lead acid battery or the lithium ion battery. You learned a little bit about corrosion and protecting from corrosion, and how we can make some oxide coatings of zinc or aluminum to make things safer and not dissolve. And then you got an intro to electrolysis and how that's the backwards of all the batteries or galvanic or voltaic cells that we've been talking about.